Earth's surface may feel solid and immovable, but in reality it's broken into massive slabs called tectonic plates. These plates make up the lithosphere and float on the softer, ductile asthenosphere beneath. Their motion is powered by mantle convection, ridge push at spreading centers, and slab pull from a sinking lithosphere. The interactions of these plates at their boundaries are the driving force behind earthquakes, volcanoes, mountain building, and the shifting of continents over geologic time. The first boundary we will be discussing is a transform boundary. Transform boundaries have plates that slide horizontally past one another. The lithosphere isn't created nor destroyed here, but friction prevents the plates from moving smoothly. Instead, stress builds up until it is released suddenly as an earthquake. These quakes are typically shallow but can be extremely destructive because the rupture occurs close to the surface. The San Andreas Fault in California is a classic example of this, where the Pacific Plate and North American Plate grind past one another. Transform motion literally offsets rivers, roads, and even entire landscapes, leaving visible scars across Earth's surface. For humans, this means sudden, unpredictable shaking that can devastate cities built along these fault zones. At divergent boundaries, plates move apart. As they separate, the pressure in the underlying mantle decreases, causing decompression melting. Magma rises to fill the gap, solidifying into new crust. This process creates mid-ocean ridges, such as the Mid-Atlantic Ridge, where the Atlantic Ocean continues to widen. On continents, divergence produces rift valleys, like the East African Rift, where crust is thinning and subsiding. Geologically, divergence builds long volcanic chains and generates frequent but relatively small earthquakes. Over millions of years, divergence can split continents apart and open new ocean basins. For us, it means volcanism, geothermal activity, and slow but steady reshaping of Earth's surface. Finally, we will be looking at convergent boundaries, where plates collide. When oceanic crust meets continental crust, the denser oceanic plate is forced beneath the lighter continental plate in a process called subduction. Here, the turquoise box represents the oceanic plate that is subducted underneath the continental plate. Subduction zones generate deep ocean trenches in volcanic arcs, as water released from the descending slab lowers the melting point of the overlying mantle, producing magma. The Andes Mountains and the Cascades are prime examples of this process. Around the Pacific, subduction fuels the volcanically active Ring of Fire. When two continental plates converge, neither subducts easily. Instead, the crust thickens and uplifts, forming massive mountain belts like the Himalayas. Convergent boundaries are also the source of the most powerful earthquakes on Earth. Locked subduction zones can rupture catastrophically. In the 2011 Tohoku earthquake in Japan, which triggered a devastating tsunami, is an example of this. For us, convergence is both creative and destructive, building mountains and fertile volcanic soils, but also unleashing some of the deadliest natural disasters. So whether plates slide past, pull apart, or collide, their motion is the engine of Earth's geology. These interactions explain the distribution of earthquakes, volcanoes, mountains, and ocean basins. Plate tectonics not only unifies our understanding of the Earth's past, but also reminds us that the ground beneath our feet is always in motion.